So my presentation is about the efficiency of broadcasting in multi-channel, multi-interface wireless networks. This is a brief outline of the presentation. I will describe very briefly what is about the multi-channel wireless network. I will talk a little bit about the channel assignment that is used in this kind of networks. And in the second part, I will be describing the problem that I'm trying to optimize and some simulation results that I performed. Well, why are we interested in multi-channel wireless networks? Well, in wireless networks, along the history, many people have tried to propose some solution to increase the throughput and also decrease the delay. So one of those solutions that works very nice is to use multiple channels in the network. Why? Because having the nodes tuned to different channels, we can see that the nodes can communicate simultaneously with two different nodes, for example. That means that a node at the same time can be receiving information and can be transmitting information to other nodes. Now, of course, to use multiple channels, will those channels to be orthogonal? In the AO211A, for example, we have up to 12 channels, but only 5 of them are orthogonal. So now, in the literature, we can find that many deployments to use multiple channel networks propose to use multiple radios. That means multiple interfaces in each node. The advantage is what I mentioned in a single channel network. For example, if the nodes in the middle want to transmit to the second node, first it needs to receive, and after that transmission is finished, it can start the transmission to the second node. By using multiple channels, the node in the middle could be receiving information from the first node, and at the same time it could be transmitting information to the second node. Of course, here we need to use two different interfaces and two orthogonal channels to this possible. So now let's talk a little bit about the channel assignment that many people have used. There are three main channel assignments. First, the common control channel. This is basically the one channel is specific used for control. So the nodes exchange control packet and say, for example, so for the next transmission, let's use channel 1. So they decide ahead the transmission which channel they are going to use. The static channel assignment is when all the radios of a node are fixed to a particular channel. And the last one, and that is the one where we are interested, is the hybrid channel assignment. Some of the radios, some of the interfaces are fixed, and some of them can switch to other channels. For example, in this case, if the first node wants to transmit to the second node, we have that only one of those interfaces is used for receiving data, and the other interface is used to transmit the data. So if this node wants to transmit to the other node, the switchable interface has to tune to the fixed channel of the other node, and then it can transmit. The problem with this mechanism for the channel assignment is that there is a switching delay that is not negligible because it's around 5 milliseconds. Of course, in hardware, it's very nice. It's in the order of microseconds. But the problem with this assignment is that there are also some software delay involved in it, because the driver has to detune with the channel where it's currently working, has to switch to a different channel. So the delay is around 5 milliseconds. So it's very important for daily sense application. Now, broadcasting. This is the problem that I'm trying to resolve. Broadcasting is, I think, the most used technique in wireless network, because it's used, for example, for neighbor discovering, and also is used for the route request when a node wants to send data packets to another node. If first has to perform a route request to discover where is the other node located. So The problem that we have in this kind of network using multi-channels is that, as we've seen before, not all the nodes are tuned to the same channel. So we can have network partitions because one node can be transmitting in channel 1, but other nodes are listening in channel 3, for example. So the solution is that the first node has to switch their switchable interface to channel 3, and then it will be able to transmit to the other node. Well, some routings and link layer protocols, I would say that all the routing protocols need to perform broadcast, and the link layer protocols also need to perform broadcast. In the solution, they are trying to, of course, those protocols work nice with relation to the throughput and the delay, but the problem is that when performing the broadcast, the way that they do that is to just transmit the packet across all the channels. That means that if we have 5 channels, for example, in the network, the node has to switch the interface 5 times. Remember that there are 5 milliseconds per each switching of the interface. So there is kind of a big delay in that sense. So I'm trying to improve that, applying some techniques, very common and used techniques using in single channel networks. Yeah.
This is the same problem I was describing, with the power line stuff earlier.
Oh.
Where you have different subbands.
Oh.
That they may be listening on different subbands. It's frequencies, but it's like
okay.
Channels. Same problem.
Okay. Yeah. Well, the way I just prove with the easiest solution that we have to achieve broadcasting, that is using a probability-based broadcasting. Actually, it makes that this technique used very nice. The main idea of the solution is that in using hybrid channel assignment, we have that the nodes have to learn about the neighbors, the channel that the neighbors are used. Of course, otherwise a node couldn't be able to transmit to a neighbor if that node doesn't know in which channel that neighbor is listening. So the hybrid channel assignment use the neighbor discovering protocol. So what I'm proposing is use that information and use some probability to decide on which channel I will transmit my packets. So I'm trying to avoid transmitting on all the channels available in the network and just selecting a subset of those channels and transmitting on those channels. The main idea is use the information that I learned from my neighbors. And for example, if I have 5 channels, what I do is in each channel with some probability, for example, in channel Y with probability 0.5, I decide to transmit or not transmit. In the next channel, the same thing and apply. And it makes that this solution works nice. And of course, with the solution of transmitting on all the channels, we will have a perfect reachability because my packet will be received by all the nodes. But sometimes it's not necessary to do that. It's enough that some of the nodes receive the packet for my goal that I want to do. Well, I will present you the performance evaluation, the assumptions. This work is related to a test bed that was implemented here in the wireless network groups. That test bed used the technique that I just mentioned. When broadcasting, it transmits the packet across all the channels. So I made the assumption that are used in that test bed. Each node is equipped with one fixed interface and one switchable interface. Only the fixed interface is used for receiving the data. Every node is aware of all the channels available in the network, and the nodes exchange hello message to discover where my neighbor is tuned. So the simulation setup, I using a static network with random topology, the MAC protocol, the AU211A. I'm using the MAX the maximum transmission rate for the channel, 54 Mbps, and I'm using 5 channels that are the number of orthogonal channels available in AO211A. And the switching delay, I'm using 5 milliseconds. This simulation were performed in the NS2 simulator. Well, this is just, here I'm trying to optimize the neighbor discovery. It's like a proof to show how well this technique performs. And it seems that even when I have a probability of transmission in each channel of 0.8, the improvement is big. So this is the number of hello packet transmission. The hello packets are transmitted 2 hops away. So if I transmit my information, just my neighbors retransmit and nobody else retransmit. Here is cumulative, and I mean by the round of hello packets. So the improvement is big, and this is the neighbor discovery. Of course, we could expect that using some probability to transmit, not all the neighbors are discovered. But we can see that after using a probability of 0.8, after 3 rounds, we have the same number of neighbors discovered that we use in flooding. By flooding, I mean transmitted across all the channels. So usually we say that we use an interval of 5 seconds or maybe something lower than that to each hello packet transmission. So we can see that after 3 rounds of hello packets, all the neighbors, every node are discovered, all the neighbors in the network. Now, this is more interesting. It's about optimizing the route request. What I did here is I have a random network with 30 nodes, and I chose randomly 2 pairs of nodes and establish a UDP connection between those 2 nodes. I use packets of 512 bytes, and the rate transmission is 54 Mbps. So when a node performs the route request, it broadcasts the packet, and everybody else has to rebroadcast that packet the first time it receives the packet. So in the previous solution, you have to rebroadcast the packet across all the channels available in the network. But here I chose in the previous slide we saw that probability 0.8 was nice, but I chose probability 0.7, and we can see that when I have 10 connections working, so I mean by 10 connections it means that 10 nodes are performing the route request. So 10 packets have to be broadcasted by all the nodes in the network. We can see that this is the average rebroadcast per node. We can see an improvement of 40%. This is very important, of course, the delivery ratio. One could expect that the delivery ratio is not the same, obviously, because with flooding, I'm trying to assure that everybody receives that packet. But we can see that with 0.7, the delivery ratio is very similar to the case when I transmit across all the channels. Indeed, sometimes it outperforms. The reason why sometimes flooding is no, one will expect that the delivery ratio of flooding be 1 always. But remember that I'm using the AO211A MAC layer, so sometimes there are collisions and things like that. So sometimes the packets are not received by all the nodes. So the delivery ratio is very similar. So it's acceptable, I would say. And also, this is important, the latency of the route discovery. The problem when you transmit across all the channels is that you are increasing the overhead in each channel. Increasing the number of packets being transmitted in each channel, that means that increase the contention in each channel. So sometimes the packet could be dropped because of collision and things like that. So using a probability scheme to transmit, of course, it reduces the number of packets transmitted in each channel, and also it reduces the contention. So the latency of the route discovery tends to be less. Now, one important point that is I need to mention here is that only 85% of the times that I run the simulation, the node discovers the same route. Because, of course, you could assume that if I'm transmitting in the whole channel, soon or late I will discover the best route. But if I transmitted in some subset of those channels, it could be the case that I don't discover the best route. But the important point here is for the cases when, for example, when you have mobility, it's very probably that you constantly need to perform route requests because the route, the node where you are communicating is out of your reach. So you will need to perform again the route request, and this technique is just at the beginning to discover where my node is located. So the delay is improved. So now the conclusions that I could say about this work is that we can see that the flooding have good, we'll expect that the flooding have good reachability, but it's very expensive. Remember that each transmission implies energy consumption in the node. The transmission could be that didn't reach the destination, so each transmission could be that it has to be performed many times because of the MAC layer retransmission mechanism, so it consumes a lot of energy in the node. So, and also it affects the latency of the broadcast transmission. And in this work, what I show is that the probabilistic approach is shown to perform nice. Of course, we saw in the delivery ration plot that it doesn't have the same reachability, but it's enough to perform a route request or to perform a neighbor discovering. We saw that after just 3 rounds of neighbor discovering, we already discovered all the neighbors that we discovered when we transmit across all the channels. And one important thing that I'm trying to do right now is trying to work in a dynamic probabilistic approach. So not to use a fixed probability as I use here, 0.7, but using the information of the channel and the number, maybe what I'm doing right now is the number of neighbors that are around me. I'm trying to set one dynamic value for each channel. So for example, I will use some probability to transmit in channel 1. For example, if all my neighbors are transmitting are listening in channel 1, of course that I will need to transmit in channel 1, otherwise my neighbor won't receive the packet. So something like that is that I'm trying to use, and also apply this technique to mobility to be more interesting. Yeah, that's all the presentation. If you have any questions.
Have you looked at these IETF routing algorithms like Ripple and RPL and things like that?
No, actually, the routing algorithm that I use here was one that was proposed in the wireless network groups.
Yeah.
It's an algorithm for multi-channel. It's based on the WCETT metric, but this algorithm was improved because the WCETT metric didn't consider the switch delay. So in the wireless networks, some class may propose an algorithm using the switching delay.
So you're using probabilities here. Is there another way to use like link quality or some kind of other measure?
Yeah, sure. Because in single channel there are some techniques that use link quality, or maybe there is some way to try to measure how far I am from my neighbors, or how close are my neighbors. I can use that information to decide, okay, I will transmit to this neighbor or not.
So we have, like measures like signal to noise ratio or something. And we'll have we'll have different channels and that type of thing. So
Yeah, of course that could be used, because if I having at the moment where I want to transmit, maybe that channel is experimented too much interface, the node could decide not to transmit. So those techniques could also be implemented.